Okay, that's not part of my script, but this work got a lot of citation already, and there are many reasons why so, but I just want to mention maybe two reasons that are particularly interesting for our work. The first reason is that injects a 3D inductive bias to an image synthesis pipeline and allows your method to reason in 3D. And the second, so once a neural representation is built, you no longer need meshes, you no longer need texture mapping material, so you can avoid a lot of labor that the designer is usually doing. Therefore, it's actually quite exciting to work with these representations. All right, so let's start with NeuROIC. NeuROIC stands for Neural Rendering of Objects from Online Image Collections. And first, let's look at what online image collections are. And online image collections are images showing the same object, but in different environments, taken in different lighting, and also with a different camera. So we have images like this. So this is either downloaded from Amazon or from internet, or we just have the object and captured it ourselves in different environments. So, but the goal is to build object representation from such images. We assume we have around 30 images of an object that we want to build. And after our network trained, we can build a relightable representations that look very photorealistic. And interestingly enough, there are some groups of objects for which this is probably one of the only ways to actually digitize them. For example, here, we won't be able to take this bust of Nefertiti and to bring it to the lab to do photogrammetry and so on. But what we can do instead, we can use thousands, maybe tens of thousands of images of humans, of this bust that humans have taken, and we can use it to do what we want. So now I'm going to go a little bit deeper into detail of NeuROIC framework again, so the level is detail is lower than in the paper. So the framework consists of three major stages. The first one is geometry. We then extract normals and remap them so they're more high quality. And finally, we have a rendering stage. So let's look at the stages a little bit in more detail. So for geometry, again, so we take online image collections, and usually what people do when they train systems like that, they run structure from motion pipelines such as CoMap. But here is actually pretty hard to do because all backgrounds are different. So we first manually remove backgrounds, and there are many tools that allow you to do this efficiently. So then, given that our use case is very complicated because the cameras are different, there are sharp shadows, there are specular highlights and stuff like that. And also we have only coarse camera poses because we can only apply structure for motions on the area where the object is and not rely on the background. We follow some prior work and use the concept of transients in our geometry branch. So the concept, we have two networks. Each of them take camera pose, and also each of them have basically our coordinate MLPs. And each of them, one of them, the static MLP has appearance embedding in it. The other one has transient embedding. So we learn this per image. And then both of them predict density and color, which we blend together to obtain a single density and color. And a commonly used approach to train such networks is usually based on reconstruction loss, but in our case, it has some artifacts such as the boundary of the object is not so good. So we additionally add a couple of more supervisions here. So first of all, we use silhouette loss, and we also found that when you should keep the ratio of foreground rays to background rays above 1/3 in training. And additionally, since we cannot do structure from motion reliably firsthand, we also do camera optimization during training of the first stage. And once this is done, we move on to a normal estimation. So usually people, a common approach here is to take gradients of the density function, and this will be your normals. But the problem here is that these such methods like gradient-based density normal estimation is that density is unbounded and can be pretty noisy because of the challenging environment. Again, so every image is from a different environment. And so the normals will be substantially misled by the density. And here you can see that, okay, I cannot show it, but there is a red arrow and there is surface. And you see that because of the density that is unbounded, the normal is not correct. So if we can just remap the density to all ones, or we can clump it or somehow bound it, we get the correct normals. So to perform this remapping, we introduce a simple but quite effective approach. So we first estimate a bounding box. So we take training images and sample inside foreground masks and extract ray and surface intersection, expected ray and surface intersection. So this way we get a point cloud. We then take this point cloud, get its bounding box, and discretize the bounding box into a voxel grid. And in each voxel, in each cell of this voxel grid, we compute the density. And then we can remap this density by bounding it. And to compute the gradients, we use a 3D Sobel kernel just to get the normals. And as you can see, that with and without remapping, there is a big difference. So without remapping, the normals are pretty noisy. And with remapping, they're much better. And we have ablations in the paper that also numerically tested. So we then use these normals and geometry to supervise the rendering branch. And here we move on to rendering branch. And here we want to estimate lighting for each input image and material properties for the object as a whole. And we use to represent lighting, we use low order spherical harmonics here. And spherical harmonics, as you might know, they work well with ambient illumination and not so much with high frequency details. But using high frequency representation in our scenario is impractical because we use images in the wild and there is noise, there are camera issues and other things. And therefore we introduce the concept of transients to the rendering branch as well. And here it makes our framework a hybrid consisting of parametric and neural network based color prediction. So with the transient component is represented by a fully connected neural network, and the static networks output the parameters of spherical harmonics, which we can then render. So the transient network gives us the density and color, and we can combine twos by linearly interpolating based on density and get the color in that way. So our framework gives us albedo, normal, specularity, and glossiness. And here I would like to show the benefits of the transient, this two neural networks here. So on the right, this one, I don't know if you see it, probably not. So this one is the ground truth. And you can see that there are sharp shadows. And this image, the top image that is static, doesn't have those sharp shadows there. They all end up in the transient component. So therefore, we actually obtained what we wanted, where sharp shadows are and end up in the transient component. So we tested it on a bunch of images from the internet for a variety of objects, and we obtained high quality neural representations. And maybe now I should answer the question why we did that. Well, because we now can compose objects into scenes, and very conveniently, an environment of a PhD student such as this one, contains many objects, many corners, so plane tracking works really well here. And it also works for regular environments, such as this one. We can obviously render the color and render the normals, and we did some simple lighting estimation here. So with a framework like that, one can actually take images from the web, use some simple tools to segment images out, segment foreground from background, and then one can train for about 20 hours and get this nice composition results. And this eventually makes inserting objects into scenes much simpler. So with the help of Neroic, one of the challenge how to create static objects representation for AR experiences is somewhat simplified. But the question is how to deal with objects that needs to be animated, such as human bodies or other objects that you would like to animate that are non-rigid. And we want to also render them backward. And traditionally, they've required rigging, skinning, motion capture. So how can we simplify this process? And in this work, in this CVPR, we introduce a new 3D representation for scenes and videos. We call it playable environments. And I would like to emphasize here that it's similarly to Neroic, it uses only images or videos we collected from the internet. So we didn't do any data collection. And also we didn't do any model fitting, anything. So it's in some sense is an unsupervised framework. And just to explain what it does, I want to maybe give you an example. So if you can imagine the last tennis match that you saw, and what would you like to change in that match? So you have a video, what would you like to change it? So perhaps you wanted to move the player to the right, and here you move both players to the right, or maybe you want to move them to the left, or you want to move them forward to the net, or you want to maybe change the camera view to show some highlight more dramatically, or maybe you want to change the style of the field and of the player. So this is what playable environments can do. It can allow you to control the style, control the players, and control the camera. And we call it playable because you essentially have buttons to press to do all of that. So therefore, it makes video manipulation and scene manipulation like playing a game. So once again, so there are some characteristics of playable environments, how we define them. We can play multiple deformable objects. We can move the camera, change field of view. We can change the style. We can copy the style from one player and pass it to the other. And again, this is unsupervised. So what we need a set of videos in which we have detected the players using bounding box detectors, and we performed some rough camera calibration using the available features. So how does it work? It's a generic framework for video manipulation, and it's an environment. So there are states of each environment. So for each object, we have a separate state. So here are 3 objects. One is the scene or the tennis field, and a state for each player. So we have a separate encoder for each of them, and the encoder extracts a state. A state corresponds, it consists of object pose, object style, and its location in the scene. So once this is done, we have a synthesis module that takes also camera pose and can synthesize the same frame. And we can train it in an autoencoder manner. So we basically, when it's done, we have a video autoencoder. So how does the synthesis module work? So again, we have a state. State has a position. Since we know where the object is, we know its bounding box, we can sample points within this bounding box. Then we represent objects in their canonical representation, and we have a bending network to bend the object to its pose. So the bending network takes the pose. And again, we have a style, another part of the state, and we pass it through adaptive instance normalization to the feature network. We do this separately for every object, and recall that there are 3 objects at the field and both players. Then we integrate the features and have a feature renderer that renders patches. This one is easy to supervise using patch-based L2 and perception-based losses. And once it's trained, we have a video autoencoder that can generate novel views of the same video. If we don't change anything, we just generate the same video, but we can move the camera around. But the interesting thing is that what happens between the frame? And what happens between the frame is the action. For example, if the action is move left, it means that one of the players should move left while everything else in the environment should stay the same. And we have an action module to figure it out what happens and how to predict the next action. And once again, so we don't have supervision for actions. Actions are inferred automatically during training. What we know is the amount of actions. I think in this case, we estimate 7 actions, and they're assigned randomly, obviously. So just to give you a hint, how does this action network operate? It's based on our previous work last year, CVPR, where we did playable video generation. So we updated the network so that it supports 3D actions. And the action is something that happens between states. So if I move left, it means that my style has to be the same. Maybe so my pose is different. So, and it's a goal of action network to understand what happened between frames. And there are 2 major things that it can do. One, it predicts a discrete action class, 1 or 7. Basically, it's a one-hot prediction. And it tells you move left, move right, move to the net, hit the ball, or do some other actions that we have. But the thing is that there is also action variability. The action class tells you what needs to be done, but action variability tells you how it can be done. For example, you can run left, crawl left, jump left, or many other ways an action left can be executed. And this is hidden in a continuous vector action variability. So once we have the action class and action variability, we pass it to a neural network, and the neural network predicts the next state. And we can supervise here, as you can see, based on the input and the output. But compared to our previous work, since this one is a 3-dimensional, it's a little bit harder to supervise it. So we introduced a more regularization here. So to train this particular module, we have L2 and mutual information between environment states. We also want to minimize the variance of player movement for each action class. And finally, we have adversarial loss between reconstructed states and ground truth states. Again, these are very rough details. Everything is in the paper, and happy to chat. But when the network is trained, we basically throw everything away and leave just the recurrent neural network, and you can physically attach a controller to this recurrent neural network, and you can play. And here we overlay the actions on top of the tennis field, and each action is colored with a different color. And you can see there are distinct clusters of actions for each of the players. Again, the cool thing is that it's completely unsupervised. And you can see that there is action move left, move right, move forward, then move diagonally back, and move a little bit to the left, move a little bit to the right. And clearly, it's very hard to disentangle clear actions such as move left and don't move forward and backward, because it depends how you sample the data. But overall, we're quite happy with this result. And now you can play. So you can play. We tested on various games and Minecraft and tennis. So you can see those actions pressed by the player and the top. So you can play both players. You could move the camera and play. So you could do it for both of these data sets, and you can change the style. So you could literally copy one style and apply it to another one, and you do it all in 3D and all at the same time, and all in the interactive way. And I think this is last slide of my talk. And so we wanted to show and make those difficult, challenging tasks, such as content creation and content manipulation, accessible for amateur creators, such as maybe myself. And in Heroic framework, we were able to learn rich and high quality object representations that can be composited back to the scene. And we did this from a handful of internet images. And with playable environment, we can manipulate a 3D video in space and time. We can move the camera, we can play the video, we can change the style, at the same time manipulating the video. And that's like exciting because it's like playing a video game. And maybe just maybe someday we'll create video games like that. And I think playable environment code is already public for Heroic. We're finalizing a couple of other things, and will be out very soon. And I think that's it from my end. We have around a minute and 10 seconds for questions.